I'm very excited to be here to talk about what we're doing in terms of using AI, especially in this NASA science domain. What I'm going to do today is going to talk mostly at high level, right? And if anybody's interested in getting into details of any of these projects, I'll be available after the talk to do so. Let's get started. So I want to start by using my experience a few years ago when I was trying to do a research on environmental justice, right? And I wanted to draw a distinction between how it fundamentally has changed, AI has changed the way we do science. So I was trying to study environmental justice related to smokes and fire caused mostly on the West Coast side, right? So typically how I would approach this is go to this fantastic system that NASA has built in terms of imagery, right? I'll go and try to look for this imagery with smoke. So I will find something like this, and then I'll turn on a layer for thermal layer, just to see if it's caused by fire. And I'll see these red dots, right? So that tells me there was a fire that caused this smoke. It's very intriguing to see that it travels so far away, right? And there's a reason for that. There's a lot of complicated atmospheric dynamics that's happening around this area that causes the smoke plumes, pollutants to travel all the way. So it's a very intriguing environmental justice use case. So what I would do after that, now I know the date and time here, right? Date and time of the event. I would go to an interface like this where I can search for actual science data. I will type in like fire, date and time, and I will get all these data values, data files, right? I will download those and do my science. So this was about 4 or 5 years ago. At the same time, one of my colleagues was trying to develop a machine learning algorithm, and he was actually hand curating these smoke plumes from a different data sets, right? So we thought, wouldn't it be nice to develop something like this, where you use those plumes that he's drawn, use that as a training data to train across the entire archive of this satellite imagery. And I could develop something like this. This is the same fire, right? So wouldn't it be even better if I can just ask the system, hey, how many active fires were there in the United States yesterday? Now you can do this, right? This is a ChatGPT example. But you can connect that with our systems, and you can actually do interactive analysis like this. So where am I getting with this, right? So the idea here is that something that used to take me multiple days 4 or 5 years ago, now you can do it in minutes. So this is the takeaway, right? Scientific process is fundamentally changing due to AI. I just show you an example of data analysis, basically, right? How efficient data analysis could be. But in reality, it's affecting every step of the scientific life cycle. So this is not the first time science has seen a fundamental shift in terms of paradigm, right? If you look at the history, 1600, it was all empirical based, right? It was based on observation, right? Johannes Kepler is a very good example of that. He studied how planets revolve around the sun, and he came up with observation that became a theoretical in 19th century, right? This was a theoretical era where Newton's law of motion, Maxwell's equations, those are all highlight of that paradigm. The idea there was that you can now do a theoretical proofs of that goes back to empirical analysis. The idea there was that it is very accurate and precise, right? But you could only do for a certain amount of theoretical knowledge. Then came the computational simulations, right? That was driven by high-performance computing. What that allowed was to scale the second paradigm. Take those theoretical aspects and scale it across time and space. A lot of that third paradigm generated a lot of data, which became the fourth paradigm, which is in the early 2000 era. This was also driven by a lot of advancement in sensor technology that helped us collect a lot of data, science simulations, and this is where the traditional statistical machine learning became very popular. And this was also called the big data era, right? Or e-science. So what has happened recently in the last 2 decades is this fifth paradigm, right? Now you have these scaled algorithms, deep learning algorithms to be specific, that can actually emulate the simulations or the observations that you used to see before very accurately. And that's where we are now. So this is a fundamental shift. As you see, it goes through, as technology advances, science seems to adapt to the technology. So in the meantime, AI has also been evolving, right? I put this specifically here because AI is also a science, part of a science, specifically computer science, right? Look, computer science goes back quite a bit in early 1950s, which was the era of Turing machine, right? Turing machine was invented there, and so was perceptron, which is the building blocks of modern day AI. Turing was known for many things, including the modern digital computer. What has happened in around 1980s is these algorithms that can learn from the data, right? And those are the days of machine learning. And it was driven by mostly statistical approaches that learn to do things by just looking at data. And it's basically replaced the knowledge-based system, which was very popular around 70s. Of course, last 2 decades have seen deep learning, which is scaled by large-scale data sets, mainly ImageNet. And it has seen a lot of progress in science, too, like folding, the estimation of folding proteins, a lot of climate simulation. All of that has been scaled by using deep learning now. What has happened recently in last couple of years is this emergence of foundation model, which are these pre-trained large models, right? And one example of that in language domain is the ChatGPT. So I'm mostly going to focus some of the results based on this foundation model today. So before I do that, I wanted to draw a distinction. This is a talk about AI for science. I do want to draw some distinction about what is AI in general and how it's different from AI for science, right? So in AI in general, we usually want to try things out, trial and error, deploy, iterate, right? In science, we really don't have that luxury, right? For example, applying AI for drug discovery, we really don't have that kind of luxury where you can iterate through observation and feed that back into the system, right? So mistakes can be very costly. Most of the time in AI, in general, we want to benchmark and beat the state of the art. While in science, science is all about understanding, right? We want to make sure when things don't work, why it doesn't work. A lot of times, AI in general, we seem to match patterns, pattern recognition, finding cats in the internet, videos, things like that. But in AI for science, we want to model these physical phenomena, right? And we do that by looking at these partial differential equations or other physical phenomena that governs the science. A lot of times when you talk about AI in general, we're talking about automating human tasks, like automated driving. Whereas in science, we want to make things more efficient for the scientist, right? Scientists are very creative. They are the ones putting together a hypothesis to run experiments. We want to make their life easy. And we do that by augmenting these repeated tasks. AI in general, in most of the business settings, we want to make things more efficient. Whereas in efficiency is one of the things, but it's not the only thing. We want to make sure that when we make decisions using AI in science, that there are major consequences that we have to consider. AI in general, also, we mostly look at specialized data, right? We're looking at image data of some sort, audio data, text data. Whereas AI for science, you have very complex data sets, right? You have synthetic aperture radar, you have hyperspectral imaging, very complex data to work with. When we evaluate AI in general, usually there's a team of internal people, right? We're evaluating these things before it gets into the out in the public. Whereas in AI for Science, we have an established process of evaluating, community-based evaluation of these AI solutions. So this was just to make sure that we are on the same page in terms of when I talk about AI for Science, we're talking about these things on the right. So in terms of advancing science using AI, there are twofold, right? One is how can you use AI and infuse it into scientific process. The other way to look at it is what AI advances are actually necessary to reach our science potentials, right? These two things. So today I'm going to focus on the first thing. How can we effectively use AI tools in science? Because I want to focus on that because I know I've worked with scientists, domain scientists. They are very creative. We want to make their life very easy to do certain tasks. And they're also very patient. I've worked with engineers, no offense to engineers, but scientists are by far very, very patient. So they are open to using AI tools in their workflow, right? So when I talk about science, it is a process, right? It's not just a product you see at the end. It is an iterative process, and it goes through like this. You have an observation. Then you try to formulate a lot of questions. Usually you do that by looking at the literature, right? You find findings from previous scientists or science research, and you have certain questions. You combine those questions to formulate a hypothesis, and you do a number of experiments. You do analysis of the outcomes of the experiments, and then you conclude and write a paper. In some cases, the data from your analysis goes back into the observation, and this is an iterative cycle, right? So let's look at this each step by step and how AI can infuse or affect this process. So I'm not going to touch on the observation because that's a given. There are a lot of AI-based observation technique that's happening nowadays. Questions. A lot of people have used large language model to mine scientific literature and figure out and establish a set of questions that scientists may answer. But let's start with the hypothesis. So as the data is growing, publications is growing, the hypothesis space is also growing, right? There are just too many hypotheses for humans to go through. This is where AI can be very helpful. It not only can put together a set of hypotheses, it can also test more complex hypotheses that human cannot put together in a timely manner. So here's an example that was published in Nature recently. It found out that the hypothesis that was devised by AI was able to find blind spots in research. Right? This is an interesting article. There are also tools like, I think it's called Hypothesis Maker, that's completely based on GPT-4. That's able to take certain questions from users and actually formulate a research plan for you, all the way from hypothesis to data analysis. So let's look at the experiment side of the life cycle. There are examples of AI being used to design candidate experiments based on your hypothesis. Another thing that has happened here is that AI can actually do some of these experiments, simulations, much faster than traditionally you could do using HPC and so on. It can also help finding the right set of papers to work or replicate to assist in your research life cycle, right? And obviously, the robotics is another thing where there is a lab. People are designing labs where actually robots do the experiments, completely based on AI. I want to show you this one example. So this is work done by our colleagues here. What this is doing is just instead of doing the experiment completely on numerical simulation-based experiment on HPC, which would take you 4 or 5 days to do a 7-day forecast like this, they were able to do this using AI to be specifically Clifford neural network based approach, which took the data for 7 months and did a forecast for 1, 2, and 7-day forecast in fairly short amount of time. I think it was 12-hour model run on a commodity GPU. So it's basically looking at the wind value on the left-hand side, which is the target, and predicting on the right-hand side at the top, and looking at the differences here. Obviously, this is not perfect, but it's quite accurate when you go in higher latitudes and on both sides, right? So this is just making these experiment really, really efficient. Okay, let's look at the analysis side. I think this is where AI has made a lot of progress, right, in terms of doing the analysis, data analysis. When you think about scientific processes, people usually associate AI with the analysis side of things. This is because we have just too much data, right? And AI is very good at sifting through all of these data. When you talk about science, we are interested in learning about these phenomena that doesn't happen very often. And that means you have to go through all of these data, right? We produce a lot of data, but interesting data is very few. And this is where AI is very good at. There's also a lot of researchers publishing scientific research experiments with different results. How can you go through all of that, right? So here's an example. Yeah. So we have, this is an example of an archive that goes 20 years back, right? So if you, shifting through all of that data by opening the file is just not feasible, right? So this is an interface built on top of AI where you can select, if you're interested in a certain type of phenomena, you can go to this interface and just select, okay, this is probably not a very interesting use case, but you selected a certain part of the world where you see dust, maybe. It's not, doesn't look very good here, but the idea here is that you select part of the phenomena that you're interested in. It gives you all the past event, right, of that. I can do a live demo of this later if needed. So similarly, I was showing the Earth science example. This is an example of Hubble data sets of galaxy, right? You can run the same algorithm that goes and indexes all of these Hubble images into these clusters that you see in the colors. And you go through that and see that all of these galaxies of similar characteristics are grouped together, right? It simplifies the process of doing science. Okay, the last part of the science life cycle is doing the conclusion, where this is where you write papers about your findings, right? And this is where large language models has done immense progress, right? It can help you synthesize the results. It can actually write a publication, write a draft of your research findings, right? There are also these AI writing agents that are becoming more and more popular now, that you can write these, you can task these writing agents to write a paper based on your hypothesis and your findings, and then you can also have agents that actually review the paper, pretending like they are the reviewers, right? So before it even goes to public review, you can have these agents of reviewers guide you in terms of reviews. All right, so takeaway here is that AI has the potential to change every step of this science life cycle, research life cycle. We can really speed up the discovery process, obviously, especially when there are repetitive tasks. Finally, what we want to do is get into this, right? We have seen a lot of emergent behavior from large models. Can AI actually generate new hypotheses by combining these complex scenarios? That's where we want to get at some point. Okay, now going back to the NASA science, right? I want to connect this with how we are using AI within NASA science. So NASA has a bold mission. We want to reach the new heights. We want to reveal the unknowns, right? A lot of that is done through a set of questions, right? When did the universe evolve, right? How is Earth's climate changing? Are we alone, right? All of these are science questions that NASA science tries to address. And we do that by this vantage point of space, right? We look outside and inward and collect data to answer these questions. And how do we do that? we launch missions. That's what NASA is really good at, right? These are our science fleet. And, this is about a year old. But these are all of our scientists looking at galaxies on top left, looking at sun, bottom left, looking at the sun, top right, and look at all the other planets, the bottom right, right? So these are all the mission names. You can see just the scale of this is amazing. Do anybody recognize what that mission is? Yeah, that's correct. So that's just one of the missions, if you see that, right? And it's not even the largest mission. So this is by the numbers, the data we collect, right? I mean, space is not the only thing we do. We launch balloons, we launch sounding rockets. There are small sat cubes, which was not there. All in all, this is to support our research. So all of these missions collect a wealth of data, right? And here's some example of some nice imagery that looks good here, is trying to answer some of these questions. These are some astrophysics example. But the idea here is that to understand sun, earth, solar system, and universe, we collect a wealth of data. This is the example of earth science. I just want to go a little bit deeper on the earth science domain because I've worked with the earth scientists for the longest. These are some of the active missions and some missions that are in extended life and some upcoming missions. So this is the portfolio in terms of data, right? So we are right now sitting at in earth science only, about 100 petabyte of data set, which results into 4 billion files. So this is where we are right now. I don't know if I can point it here. I can't. But it's growing exponentially, right? In 2019, we'll reach about 600 petabytes of that data. So this is just beyond human analysis capabilities, right? This is where AI is going to play a big role for us. This is a nice article from National Research Council. So I told you earlier that NASA has this mission, but they actually indicate NASA is turning into a knowledge agency rather than a space agency, right? Because they've collected so much data, and this data lives beyond the mission's life cycle, right? The challenge now is how to manage the overwhelming data and converting that into knowledge. Okay, now NASA AI, right? How is NASA science using AI? So it's been used on many different things, all the way from image analysis. So this is an image on the top right is collected from Solar Dynamics Observatory, SDO, from Heliophysics Division. So over time, the image has degraded because of sensor characteristics, the surroundings, and so on. And the bottom row is the corrected degraded images using machine learning algorithms, and obviously validated with science. Bottom left, you see the Mars rover using onboard AI to find the optimum landing site. And in planetary division, they've also used AI to actually discover new planets. So this covers a broad range of AI activities that NASA science has used. So all of the community that we support, they publish their findings in literature, right? So we wanted to see what the trend is when, in terms of AI adoption. This is general science. We're just looking at, this is very unscientific, by the way, so don't put it in publication. This is me going and trying to just do simple statistics on archive. So when you look at this general science, right, you filter by general science and AI terms, this is what you see. After deep learning in 2013, there's a massive spike in terms of AI-related publication. This is a % normalized value. Now, if you compare that with NASA science, there is a general trend that's upward as well. It's slightly lagging behind, right? But overall trend is good. This is, I don't know what happened here at the dip, but I think, no, maybe COVID, I don't know. When we also look a little bit deeper, much of the progress or publication has been in the supervised learning algorithms. So supervised learning, very simple, high level. You have a science data, you curate that science data to create labeled data, you train the model, right? And you try to iterate over that. If you don't have enough, you create more, or you clean. And ultimately, you deploy that model, right? So you can use it, community can use it. And over time, you'll have to update that as well, and you have a model. This is how community has used it until 2-3 years ago. This was by far the dominant way of using machine learning within NASA science. And we funded a lot of stuff, a lot of effort to curate the training data sets, to actually create models that are task-specific, and we've had a lot of success there. This is some of the work done by community. A lot of work has gone around satellite imagery that are relevant to societal benefit. During COVID, a lot of people developed these AI-based indicators to look into economic indicators, counting the ships, looking at contrails of the airplanes. There are also some societal benefit applications like marine debris segmentations. And people also developed labeling tools so that people can actually scale some of these algorithms. Some of these algorithms that have been developed for one domain has been easily transferable to another. So this is an example on the left is used on Earth science imagery, satellite imagery. The same approach was transferred to a Hubble telescope images where they were able to cluster these images based on similarity. And this is the other way around, where something that was developed for Earth astrophysics division was readily used on the Earth science division. Okay. Some of these applications are very small scale, but we have also done a lot of high scale examples of these supervised learning approaches, right? This is an example of actually literally counting every single tree in the Sahel region of Africa. So they actually came up with 9.9 billion trees that when you look at Sahel region, right, you don't necessarily associate with trees. But it turns out there are these individual trees that are hard to see, but when you apply high-resolution satellite imagery and AI, a lot of the work actually went into curating the hand-labeled trees. So scientists actually went and basically hand-labeled these trees on satellite imagery, 89,000 to be accurate of them. So this is a massive effort. And turns out that when you do that, you can actually look at the carbon sequestration from these trees and do additional science with this, right? Actually figure out the climate change aspect of these trees. There's some work people have also done in taking some of this research. We do a lot of research, also in production, right? And usually this is where everything ends, right? In terms of science, you publish a paper, but AI to be practically used for societal benefit, it needs to go to last mile, right? When you actually deploy these AI solutions and interpret the output so that society or public can understand it. So here's one example of that. So this was a group at Marshall who did this work. I was part of it too. Looking at satellite imagery and actually estimating the wind speed based on just that, right? Just that, because there is an issue currently that this is very subjective. People look at those images on the left and they try to associate a pattern with that. National Hurricane Center, people at National Hurricane Center actually do this. There are different forecasting locations. They actually interpret the image differently because this is a human doing it, right? So this is an approach to consistently do it objectively. So as you see, the algorithm suffers a little bit in the beginning when there's not a good pattern, but as the intensity goes higher and higher, it does a fairly good job. The reason I'm showing you this is this was the research that was done. The idea was now a group has taken that and put it into production, right? So if you look at during the hurricane, you can actually go into this interface, look at these hurricanes, and look at the actual the forecast and the predictions. Anyways, let me move through there. Okay, I talked a lot about success of the supervised learning, but there are limitations. Right? We ran a workshop 4 years ago now to bring in the community together, especially focusing on the Earth observation data. And there were two main limitations that people reported. Training data, obviously, large-scale training data is a big bottleneck to do science with AI. And these models are very task-specific. They don't generalize across different tasks, right? It was very difficult to do that without redoing the algorithm or training data set again. So good thing is recent progress in AI kind of addresses these two challenges. So, and that's related to the self-supervised learning aspect, right, where you don't need training data set to train machine learning algorithms anymore. And you can do this at scale. And this is possible because in 2017, there was a paper that was published on transformers. It was called Attention is All You Need, very good paper. What they figured out, what that paper highlighted is this notion of keying in on important part of the data over time, right? And that's the transformer architecture. What that has allowed, at least right after that came out, a year after that came out the BERT language model, which is based on that architecture. And nowadays you can't go by every month, any month with new large language model. You see the evolution of that right in the top. This is where ChatGPT sits. The vision side of things is lagging about 3 years behind. There was a vision transformer paper in 2020, and that has generated a lot of vision foundation model, which I'm going to talk a little bit, and also the Prithvi, which is our work in developing the foundation model. All right, what is a foundation model? Right, so foundation model is this large-scale, basically neural network that's trained on unlabeled data. And the idea here is to create a knowledge base that can be used on multiple different tasks downstream. Another aspect of this is that since it's trained on so much data, it has a broad understanding of the processes that are captured within the data, right? Which allows it to be applied to multiple different types of tasks. And the final thing is that it substantially reduces the need for this training data set that I was talking about earlier, right? Because now that it learned the broad knowledge about the scientific processes, you only need a small set of data set to actually train your new algorithm. So with that, we started a foundation model effort, geospatial foundation model effort with our flagship data set called Harmonized Landsat Sentinel. This is one of the most popular data set, optical data set that we have in our archive. And building foundation model is not an easy task. You need lots of, like I said, it needs to train against a broad range of data sets. And it requires a lot of computation, right? So we partnered with IBM Research to build this because they had the resources in terms of computation and this niche AI expertise that you need. And the initial version was not even big. It was 100 million parameters. In today's day and age, that's fairly small. I'm not going to go into details of that, but I'm going to show you some results based on that. So we have applied this foundation model on, at least before we published into Hugging Face, which is the open repository of AI models. We applied this into 3 different scenarios, 3 different use cases. And in all of those use cases, it was able to beat the benchmark or reach the benchmark with far fewer training data sets. That's exactly what we wanted to do. So here's some examples. So in the top left is the example of, I think it was the flooding in India. And the segmentation example of using the same model, fine-tuned with very small set of images, showing it some examples of water versus non-water, or flood pixel versus not flood pixels. Here is an example to the right, is the burn scar from Maui fire. It was also fine-tuned with a few examples of that, and does fairly well. The one that doesn't do very well is the crop. Multi-temporal classification is obviously suffers from some few artifacts. So what that means is it needs more fine-tuning data sets, ground truth data set to train more. So all 3 examples built on top of the same foundation model. So how we plan to use this? This is how we want to use it, right? When we want researchers to come, look for all these events, or go in there and look at all the, because Earth is an integrated system, right? When there is sea level water, there's water versus fire versus air pollution, all of those are connected, right? We want people to come into one integrated system and be able to do this interdisciplinary science. Obviously, there are challenges. Through our exercise, this is not new news, right? But AI today is very expensive, right? You have development effort, you need expertise, this niche expertise in data science and engineering when you want to put it in production. You need a lot of curation aspect to create this labeled data set. Obviously, for science, you need rigorous scientific validation, like I showed earlier in that AI for science chart. Infrastructure is a big component of this. The reason we partnered with IBM Research was for the very reason. And the data is growing, so you have to store it somewhere. Operationally, you have to monitor over time, right? Things change, physics change, land change, everything changes, right? So you have to adapt with new data set. In some cases, you have to scale it with new data set. And there are also compliance now that are being handed out to us, right? There are regulations that we have to abide by. So the 100 million parameter example that I gave. So I have some numbers in terms of how much it cost. So the labor, the expertise in itself cost us about $2.5 million, right? When we did the math for the labeling, data labeling aspect, it was about $5 per label, and you need about tens of thousands of these labeled data set. The computation was around 130K for the 6-month effort. And if you want to run this operationally, you need powerful GPUs, right? The example that I showed where you can do all of this inference at real time, those are powered by GPUs, right? So you need all of these costs. I don't even have numbers for these other aspects. So it's expensive, very expensive. One other challenge I've seen is, this is a snapshot from, screenshot from a Wired article, which says that machine learning is being used within science by people who actually don't know the foundational knowledge of machine learning, right? Which is a problem, which creates a reproducibility crisis. In some cases, they have examples of misleading conclusions. So what I'm trying to say here is that foundational knowledge of AI is critical if you want to get to applications of AI within science. Okay, and this is not news. Ethical issues is across the board in AI, right? And science is not immune to that. This is a work we funded in terms of bringing communities together on how we can come up with best practices and checklists of ethical AI for science. All right, I'm not going to end in bad notes, so I also have some opportunities with these pre-trained large models, right? Which is basically the foundation models. What we're seeing our community do is putting a more emphasis on this small data set. I talked about all the big data and everything, right? But more and more, the small data is being used by our community more often. By small data, I mean these highly curated data sets that are being used for creating an application on top of these pre-trained large models. So this is clear, right? This is a nice, really nice paper by Kaplan, which says that foundation models or pre-trained large models, they scale very well with data and compute, right? Which results in larger parameters. So let me show you an example, right? Everybody knows how GPT evolved. It was trained on everything on the internet, basically, right? So that's how GPT-2 came about. Then they added more data, and it became GPT-3. And they added label data to create ChatGPT. Label data here means that this is based on technique like reinforcement learning with human feedback, right? They added human feedback to it, and finally came up with ChatGPT. And now we have done this, right? You can you can customize this with your own data, own business data, or science data to create your own GPT. So what is the takeaway here? Data is a differentiator, right? The model really hasn't changed here. It's the data that has advancing this model. Maybe more close to science is the foundation model. So, right, we have a raw data, science data. We do some pre-processing. We do some cleaning, we subset, we throw out garbage, all that stuff. And we apply this transformer architecture to create foundation model. So once you have foundation model, you can do a number of things. One thing you can do is zero-shot learning. What that means is you basically ask the model to do or do a task that it has never been trained on before. Right? An example is asking ChatGPT to write a poem or something. Right? It's not been trained to write a poem, but it knows how to do it. Another example is few-shot learning. This is where you should give few examples, right? 4 or 5 examples, usually less than 10, so that you get the best out of the model, right? You get what you get to model to tune it to those examples. And the third thing is actually fine-tuning. This requires a little bit of work. What you're asking here to do is basically foundation model is a set of weights, right? You're providing it some training data set against that weight to transfer the knowledge into this new task. And those are the examples I showed earlier of burn scars and flood. So what does this really mean? With small amount of data, you can come up with new customized AI model, right? All of these end up being a model of your own. And you can put an API on top of it or whatever you want to do, and it becomes your model. That's your GPT. So what's happening within the science is that these building of the foundation model, this you can't build by yourself, right? This requires a big collaboration. But once you have that, individual researchers can go and develop this own using a small amount of data. That's what I talk about, the value of small data. These are unlabeled data. You don't need to do anything. These are science data that's available, right? This is a small data set, which is curated. So that's the fundamental shift that we're seeing. Did anybody expect me to do coding today? So I'm going to attempt it, okay? Just to show what I just mentioned. I have a number of notebooks here. How much time do I have? I do have time, okay. All right, okay, it's asking me to reconnect, so I'm not sure if it'll work or not. So here's an example. I talked about earlier environmental justice, right, use case. So there are different classes of environmental justice. You can have water availability, food availability, there's human dimensions, disaster-related, a good disaster-related environmental justice use cases when, we've seen this actually. There was a Hurricane Ida caused damage around New Orleans, right? And certain communities recovered really fast, and certain communities did not. And you could tell that by looking at the blue tarps on the top rooftops, right? Blue tarp on rooftops stayed there for quite a bit of time in certain areas, and you can observe that using satellite observations. So that's one good example of detecting these blue tarps using AI techniques and surfacing the issue of environmental justice. So here's an example of all of these snippets of paragraphs from different sources that relates to certain environmental justice. So let me run through this. Should I? So I'm loading that spreadsheet that I just showed. Okay, so there are a number of these language models that are available on Hugging Face, which is the repository of models, right? There's our model. The NASA impact is where I'm from, and we have developed our own model there. So for the sake of this exercise, let's use a very simple BERT model. So one of the things I'm going to do is just straight out of the box, I'm going to fine-tune it, the example. Fine-tuning takes a lot of time So I'm going to skip the training part here and show you some results, right? So the result of fine-tuning here is, given this, it tells me this is extreme heat and predicted is extreme heat, so that's correct. So it gets fairly good accuracy across this, right? So I'm not going to go through all of that. So this is a fine-tuning example. Can you see it? Yeah, you can see it. Okay. You can also take ChatGPT or OpenAI GPT-5 directly and do something like this, right? So this is an example of few-shot learning. So I'm giving it few examples, 1, 2, 3, 4, 5 examples to tune it. Remember, I haven't trained this model at all, right? This is just straight out of the box. I'm giving it 5 examples, and it gets up to 54% accuracy with the spreadsheet that I had. Sorry, that was not the fine-tuning. That was zero-shot learning. The fine-tuning is this one. Few-shot learning is this one. The 5 examples, this is the place where I run that, right? And with that, I get up to 60% accuracy. So slight improvement with 5 examples. So basically, this is the result, right? If you just use straight out of the box fine-tuning, you get 94% accuracy. With no example set at all, I get 54% accuracy. With 5 examples, I get 60% accuracy, right? So the need for this data set, highly curated data sets, is going lower and lower. Earlier, I was talking about the fire use case on making our scientific process more efficient. So you can actually build something like this, AI agent for fire, right? So I can tell it to take a role of something, right? I told it to be an AI research assistant that answers the query that the user provides from this system, right? NASA has a fire information system. So I want to actually have a chat with that. So today is this date, you take a role of this and do certain things, right? So I asked, provide me daily time series plot of nighttime fires in California from the January 1st to 9th. So it comes with this plot. I hope I'm still connected here. Let me see what happens when I do Alabama. Hopefully fewer fires than California. I didn't compare, so I think it looks fewer. Except for January 6, 2023. There were about 40-some fires. But anyways, you can do these kind of things really fast, right? Earlier, I didn't show this very well, but this is an example of actually analysis that leads into experimentation side of the example, right? So this is an example where you can come. Let me zoom in. Let me take an example of maybe some smoky areas. And it does fairly well, right? It tries to find the same pattern across 20 years worth of data. And the good thing is that once I have that, I can do climatological analysis like this, right? Over time, I can look at if there was a hurricane image or tornado image, I can look at how many times it occurred over that area over 20 years. And you can have a climatological analysis in 2 seconds. All moving towards making science more efficient. All right, I don't want to bore you with more coding here. All right, so earlier I talked about this, right? Supervised learning. This is how we've been doing AI for science for the last decade and a half. What has changed now is this tuning on smaller data set. Basically develop prompts and deploy. Those are the examples I showed. And you iterate over time, just like you would do there. So the takeaway from this foundation model and data is that foundation models are more data-centric than model-centric. You just need to build one model, right? After that, it's the data that matters. Eventually, what will happen from the cost experiment, I think the cost will be much lower if we build these thematic area foundation models or data-specific foundation model over time. And for us to benefit from the science foundation model, obviously the data is open, it's science quality, right? What that allows, unlike these black box closed model like you would see OpenAI or something, these are not transparent. You cannot trace it back, right? And those are reusable, because in science we need reusability so that people can take your results and do their own science with it. Obviously, it's tied to the volume of data that you feed in to build the model. And also, if there is biases in the data, it amplifies that bias, so you have to be careful with that. The human input is very critical. The ChatGPT example you saw, right? Going from GPT-3 to ChatGPT was all human feedback that actually improved the results. And obviously, it's not a snapshot. You have to keep on feeding new data sets so that it stays current. Okay. So far, I've talked about how AI can help science, right? But there are AI advances that I think can help realize some of our science goals that we need to work on. So this is purely on the AI side. What can you do? AI is basically algorithmic data, lots of data. But we need algorithms that can learn from small data sets, less data sets, right? Foundation model takes a lot of data set to pre-train. The very notion of what data is important to keep versus what to throw away, right? That's a data management task that we need to solve. Across science, we've seen progress in each of these domains. I think AI will really benefit the science community if those tools are cross-disciplinary. Tools that are developed for one science domain can be used for other domains. There's a lot of optimization techniques. Even with our exercise, we saw that we were not keeping our GPUs very busy. Right? That's because we were spending a lot of time moving data from one GPU to another, CPU to GPU, data center to data center. We need to solve that problem. Obviously, ethical and explainable AI. Like I said, scientists are very, very patient, but we need to be able to explain what is happening within AI. And ultimately, we want to get there, right? With the help of advancement in AI, can AI help us find new hypotheses? Obviously, finally, it has to be affordable. Right now, it's just too expensive. Additional takeaway. I hope I convince you that AI is going to change every step of the science research lifecycle. The outputs that are coming out of this AI for science activities need to be responsible. They need to be transparent. The exciting thing is communities are building these open source, large-scale pre-trained model, which benefits the science. Right? Now scientists do not have to spend a lot of money or effort in curating these large-scale data sets. They can work with the small data sets in the lab settings. A lot of the AI in general, progressed because of the open tooling and open models and so on. Right? We need to keep that momentum going in terms of AI for science as well. One thing I cannot emphasize enough is this need for foundational knowledge. Building any of these models, you may have a hit here and there, but for somebody to reproduce your results and not lead into misleading conclusions, you have to have foundational knowledge. You have to have a team that includes foundational knowledge. And infrastructure and ecosystem development, I think we need to have solutions around, continuously evolving solutions around hardware and libraries and data that goes along with the whole ecosystem. All right, this is my final slide, I think. From AI and science perspective at NASA, we look at it as a tool that has unlimited potential. It must be built responsibly and safely. Safety is one of the trademark of NASA. And for science, we want to do everything in the open, right? It's all about building knowledge, understanding, and we can't do that without being open. One thing we realized is how you use it make it a lot of difference, just like any other technology, right? You can put a model in the open, but how people use it make a big difference. Obviously, rigorous and careful evaluation, that's a must. We have also seen that diversity in terms of expertise in the team that goes into building these models is key. I'm not talking about scientific expertise and domain expertise and technical expertise, but also the stakeholders that are going to be using this model. Ultimately, going back to data, that was the theme of this talk, right? Data is very valuable. All of our missions are there to collect data and generate more data, right? Our goal is to maximize the value of NASA science data. Thank you.
Hi. Thank you for the presentation. It was really good. I don't think you used the term specifically. Maybe I missed it. But I just wondered if you could talk about the impact of SLMs versus LLMs, especially since you did focus so much on the need for be able to use it with smaller data.
Yeah, that's a good question. I think more and more it's becoming, so I can talk from my some experience. We started to work with these LLMs and compare that against, they're very good at general things, right? When we wanted to apply those into very domain-specific, science domain-specific things, they did not do very well. And there are several approaches to address that. You can either feed in your own data and keep the general aspect from the large language model. That does fairly well. But does it do as well as SLM where you just train it with your own model, right? That is yet to be seen. I think what the large language model do provide is this general notion of generality, right? There are techniques like, I'm sure you've heard of retrieval augmented generation, where you can actually constrain your results based on your corpus, what you feed. But that part of the research is evolving so fast. I think if I have to answer that with one sentence, I would say that a collection of small models for specific tasks still beats the large language model.
Great presentation. My question is on validation and verification. Mm-hmm. So you guys are known for doing rigorous validation and verification for software that goes into space. Mm-hmm. You cannot rule out any edge cases. Now you are talking about these type of foundation models, large language models. What type of validation and verification techniques that you are thinking about are how you are transforming the classical validation and verification techniques that are originally developed for software and sort of bring that to these type of models?
A very good question, yeah. I think one of the things that we do provide from NASA's side is the expertise in science, right? A lot of these building the foundation model aspect, I think the expertise we are leveraging from the external sources. What we do provide are these years and years of science knowledge that are either captured in the traditional benchmarks, papers, publications. When we started doing these development of foundation model, we actually made sure that we had at least 5 different downstream tasks lined up ahead of time with experts in that field. Like you saw the burn scar and flood, we had experts from those fields as part of the project. And they came up with the evaluation set and the existing benchmark, and that guided the formulation of the foundation model as well. In science, it's a little bit different than how you framed it. That's very true on the space exploration side. That is very rigorous. Science is still science. We publish our results, benchmark. When you do need to put that into production, then additional rigorous evaluation goes into effect. But building the foundation model, we made sure that it was a foundation model, right? Otherwise, it's a bespoke model. We want to make sure it worked across different applications and beating the benchmark, and that was our evaluation. For the language model side, we actually asked each division, there are 5 divisions in NASA, to come up with their suite of evaluation set. And one of the things we have done as part of releasing the model is actually release the evaluation set as well, because you know these language models will change. You cannot develop new evaluation set every time there's a new model. So if there's a consistent evaluation framework, then we can test GPT 100 or something, right, with the same evaluation set. Then you have a consistent benchmarking. So hopefully that answers your question.